I get going with new stuff, does anybody have any homework questions? There's one homework question that I want to talk about, because if you don't have questions about it, most likely you just haven't gotten to it yet, I think. So that is, let me pull it up here. So this assignment is resistive circuits. And there's a few questions just jogging your memory to start the assignment. And then there's some where you have to calculate the current and the voltage and the directions. Well, let's do 13 and 15. So I mentioned this in class, but I didn't do an example in this form. So let's say that we have a circuit like this, and we want to calculate the current and the voltage. So we want to calculate the current going through that resistor and the voltage across that resistor. And instead of using a battery as the power source here, we're using a voltage source and a ground. Okay, so the effect of that is it's the same thing. This behaves the same way. So it's equivalent to if we had a battery connected to a resistor, and this battery was 5 volts, and our positive was here and our negative was here. Okay, so notice that the voltage difference, since the ground, we're thinking of that as 0 electric potential, this is plus 5 electric potential compared to that ground. So it has the exact same effect as a battery of 5 volts. This is 850 ohms. And so remember that the electric potential is the same along any wire. If you don't have to pass through any devices to get from one point to another, the electric potential doesn't change. And so we can think of the voltage across this resistor as the positive over here, the negative over here, and the voltage is 5 volts. Okay. Now, in a resistor, we know that the current always goes in the direction from the positive to the negative. And so we know the direction of the current through that resistor is this way. And all that's left is using Ohm's law to calculate the magnitude of that current. And so Ohm's law says 5 is equal to 850 times the current. Then do that division, and the current is 0.005882 amps. Or if you want it to look a little cleaner, move the decimal point 3 points over for milliamps. And so this is 5.882 milliamps. One thing that it asks you for in one of the later questions is to go back and calculate the power dissipated in each one of these resistors. And it tells you how to do that in the problem. But the power in a resistor or the power dissipated by a resistor is the current times the voltage. Keep these in SI units and it'll give the power in SI units. And the SI units for power is, so the SI units are watts, or capital W. Okay, so what's the power in this resistor? We have 5 volts times, we can't use milliamps, we have to use the SI units. So this is 0.005882. And so that is 0.0294 watts. And there's a reason that that's important to be able to calculate that power dissipated in a resistor, because the thing that damages resistors is power. Resistors are super cheap. It's not like you have to really worry about burning out resistors, but this will tell you if a resistor is going to be in danger of being burned out. All of the resistors that we have can handle a power up to 0.5 watts. And so if you do this calculation and that's, if that's well under 0.5 watts like this is, then everything's going to work. If it's significantly bigger than 0.5 watts, as soon as you connect this circuit, that resistor is going to turn black and it's not going to work anymore. And the current will stop flowing through the circuit because the little wire inside the resistor just snaps and burns it out. Okay, then the second question I wanted to go over is this one. And this, a lot of you will probably have LEDs somewhere in your robotics project. It won't be like the main thing in your robotics project, but LEDs can be useful for just signaling what mode you're in with, like, is it turned on? Is it running? Is it this or that? So they're pretty useful in a lot of cases. And this is the simplest way to do calculations to get ballpark ideas about the current and the voltage in your circuit if you have LEDs. So, okay, the idea here is we have a circuit that has not just a resistor, but it also has this LED and then the battery that's powering it. And the simplest, not totally accurate, but accurate enough for most applications, way to figure out what's going on in a circuit with an LED is to think of that LED as having a certain voltage, but no resistance. So don't treat it like a resistor. Just treat it like something that has a given voltage. And how do you know what that voltage is? You can hook up your LED to a circuit like we did yesterday and then just measure the voltage. The first thing we're going to talk about today is using multimeters to measure voltages and currents. Okay, so we know that, so the positive terminal of the battery is on the left, which means the polarity here is going to be this way. And the polarity of this LED is always going to be in the direction of the current flow. Remember, current can't flow this way in an LED. That's what that line means there. Current can only flow in one direction. And we're saying that this one has a voltage of 2.5. So I'm going to write the voltage here as 2.5 volts this way. Well, now you can think of this as just kind of like another battery in this circuit. So how do think of these two batteries as working together? Well, we can think of, I'm going to just arbitrarily make up electric potentials for this. I'm going to just call this 0.0 electric potential. That means that over here on the other side of the battery, there's an electric potential of +9. Since this point that's at 0 volts and this point over here have no elements between them, it's just wire, those have the same electric potential. So we can think of this as 0 volts. Since we know that the left side of this LED is 2.5 volts higher than the right side, we can think of the electric potential here as being 2.5 volts. Okay, and so now we can think of, now we can finally do this calculation for this resistor. We can think of this as having an electric potential of 9 volts. This is having an electric potential. So we figured out what the electric potential is here on the same wire as the right side of the resistor. So we'll call this 2.5 volts. And so what's the voltage across this resistor? Well, it's the difference between those two. So 6.5 volts. Anybody have any questions about that right now? So I would recommend that, I'm going to finish this problem, but I recommend that when you work on this homework assignment tonight, try to do that by yourself. Try to think through it. Just understand the reasoning there. So now this is a resistor. It behaves like all resistors. The current goes in the direction of the voltage drop from the positive toward the negative. And the magnitude of that current comes from Ohm's law. So Ohm's law says 6.5 is equal to, so now for this LED to work, we want the current to be 20 milliamps. There's one other thing going on here. We're using Ohm's law, and Ohm's law refers to resistors. Okay, so we know what the voltage is across the resistor. We know we want the current through the LED to be 20 milliamps. So I'll write that here as 0.002 amps. How do we know what the current is through the resistor? Because if we don't know the current through the resistor, we can't use it in Ohm's law. Ohm's law, if the current is 0.002 amps here, but it's 0.006 amps here, what matters is the 0.006 amps for Ohm's law. Okay. So how do we know what the current is here? There's a key thing going on. These two are in what's called series. And all that means is that any current that goes through this one has to go through that one. There's no other option. There's no other path. And as long as current doesn't have any other options, any current that goes through one has to go through the other. Those currents have to be the same. Okay? It's like if you're trying to go through the tunnel on 394, that horrible tunnel on 394 East, you know, well, what slows you down is let's say that turnoff, you know, but that traffic can't go anywhere for the 200 yards before it, or sometimes a mile before it or whatever. And so the current of traffic going through that bottleneck turnoff is the current of traffic half a mile away or whatever, because that traffic can't go anywhere. It's locked into that place. Some traffic jumps ahead or whatever, but electricity can't do that. It's too dumb. There's no zipper merge in electricity. Okay, so that is the reason that now that we know what the current is through this LED, we know what the current is here. So Ohm's law says the voltage is equal to the current times the resistance. And now we can solve for that resistance that we want there to have that, to give that LED the current that it needs. So R is equal to 6.5 over 0.02. And so that's 25 ohms. Oh, nope, that didn't seem right. 250 ohms. Nope, that's not right either. 6.5 over 0.02. 325. So it's basically exactly our 330 ohm resistor that we have in the kit. And in electronics projects like this, you're almost always, I'll make this 325. You're almost always just trying to get these currents and voltages into the right ballpark. These devices have little ranges that they can operate under. So as long as you get into the ballpark, that's plenty good enough. An LED, for example, if the optimal performance comes at 20 milliamps, you can make it work from 10 milliamps to maybe up to 30 milliamps before it starts to cause damage. So as long as you're close to that resistance of 325, it's fine. Anybody have any questions about that one? So if electric current that goes through one device has to go through another device, those devices are in series. And they have to have the same current. Okay. What would be an example of two devices that aren't in series? So let's say that we had something. We're going to hopefully get to this today too. So let's say we had part of a circuit that looked like this, and let's say this is 330 ohms, this is 1,000 ohms, this is 10,000 ohms. Are either of these two in series with this one? I think I can sort of understand the thought process there, but the answer is it's just a matter. The only question is, does electricity that flows through this have to go through this? Picture one little electric guy going through this one. Does he have to go through that? And the answer is no. He can go this way, and some of them will, and so if there's a choice like this of where to go, then you can't assume these are in series and those currents are different. Okay. So this is not in series because the electricity can, let's say it has options. Okay. Yes.
By those currents, do you mean the current on the left?
Yeah. So if you, if you think about, if someone says solving a circuit, what it means to solve a circuit is to know the voltages and the current for each resistor. And so if you calculated the current in this one, it would be different than the current in this one and would be different in the current in this one. These two also aren't in series because you can imagine a path that electricity can take here that doesn't go through here. And so all three of these, we would expect to have different currents. Okay, and these two are what's called in parallel with each other, and we'll talk about that hopefully later today. Yes?
Can you give an example of something that would be in series?
Yeah. So if we're talking about resistors, these resistors can be anywhere along this wire. So let's say we have 9 volts here, and this is 330 ohms, and this is 1,000 ohms. So now the path of the electric current is locked in, and so the currents through everything have to be the same. Electricity doesn't have, electricity can't go into a corner and hide. All it can do is just keep moving around that path. If you only give it one path, the current's the same all the way along it. So this is resistors in series. Any other questions about that? We'll talk more about resistors in series in a second, but the key thing here, and I'll bring this up when we get to that, is that it doesn't just have to be resistors. Any devices that are in series with each other have the same current because that electricity just doesn't have anywhere to go and hide. Okay. It just has to keep moving, Have you ever been at the state fair on a busy day and you're trying to get into what's like a busy place, Sweet Martha's, yeah. If you got in line at Sweet Martha's and you tried to just stand there as the line moved, you wouldn't be able to. The line behind you would push, and so if you're locked into a path, everyone just has to go at the same speed. That's what series is. All right, so now we're going to talk about multimeters. So We did, last time we used LEDs to sort of see what was happening with the electricity. First we made that circuit that didn't have an LED in it. And you just kind of had to take my word for it that electricity was flowing when I said it was. Because we couldn't see anything, we couldn't feel anything. Then we put the LED in. But there's another way, and with the LED, it turned on when you did it right. So you could sort of see whether electricity was flowing. But there's another way to measure what's happening with the electricity, and that's to use a meter. And so that'll come in handy a lot of times on projects, just being able to measure what the voltage is, what the current is. So these multimeters can measure 3 things. And some of them actually can measure a 4th thing, but it's not something we're going to use in this class. So they can measure resistance, voltage, and current. And voltage and current are going to be the most important for us because those are the things that determine whether a device functions or not. And there are really 2 key things to remember as you use these multimeters. I'm going to write them up here first. Then we're going to get the multimeters, do the things, and I'm going to keep reminding you of these things. But whenever you use a multimeter, these should be the 2 things that you have in your head. So these are the key things to remember. When you're using multimeters. The first one is if you're measuring voltage, build the circuit that you want to measure. And then just use the meter as an observer. So you don't change the circuit, you just add the meter. And so let me show you what I'm talking about. So for example, to measure the voltage in this circuit, the voltage of the resistor in this circuit, okay, so let's say that our circuit is, we have the 9-volt battery. I'll put the resistor over here. Now, if we build this circuit, electricity is running, and now we take one lead of the meter. So this will be our meter. And we'll put it on one side of the resistor, and we'll take the other lead and put it on the other side. And this would be the positive lead and the negative lead. And this meter now would tell us what the voltage is across that resistor. Okay, so that's to measure voltage. Voltage is very unobtrusive. It doesn't want to influence what anything else does. It just wants to watch what's happening, okay? Current is different. So to measure, this is the second important thing. So to measure current, build the circuit you want to measure. Then once you've made that circuit, make a break in that circuit. So break the circuit at a point that's in series with the device you want to measure. And insert the meter into that break. Okay, so you can't just, if you're measuring current, you can't just take that meter and put it on top of a working circuit. You have to break it and make that meter part of the circuit. So let me show you, in this case, how that would look. So for example, to measure the current through a resistor, okay, so there's the working circuit. Electricity is running through this circuit right now. Now we're going to make a break in this circuit. Oh, God. Don't do all that. So now we're going to make a break somewhere in series with this resistor. And we're going to connect the meter into that break, where this is the positive and this is the negative terminal of the meter. So all that current has to go through the meter for this to work. Okay? If you don't do this, it will almost always instantly blow a fuse in the meter. And how much trouble do you think it causes for our department if you blow a fuse in a meter? Almost none. we have a giant jar of fuses, and someone just has to go get one and pop it out of the back and put it in. But it's still a little bit of a nuisance if it happens over and over again. And if it happens to you, your meter doesn't work anymore, and then you have to go get another meter, and you have to hope that we're replacing the fuses. If you keep this in mind, that just won't happen. Okay. So those are the two main things that you have to remember. Okay, so that's the easiest one. A lot of devices have resistance that varies as the current goes through it. So at different amounts of current flow, you'd measure different resistances. Dedicated resistors like you have in your kit are designed to be the same value of resistance no matter what current's going through them. And so all you're going to do to measure the resistance is, so if this is your resistor, and this is your meter. Notice that there are ports at the bottom for cables, and then there's a dial in the middle for all these different settings. And the dial in the middle is broken up into sections. Like notice on the upper left are all the voltage sections. Then there's what would that be? I don't know. There's one with a C on it. There's one F for farads for capacitance. On the lower left, there's a section for currents. You know, it has amps on it and then some milliamps and stuff like that. And then over on the lower right, there's an omega sign, and that's the one for measuring the resistance. And what you're always going to want to do is so start out with the dial at the off setting at either the top or the bottom. Notice the two zeros. And when we put, okay, and for any measurement, the negative is going to go into that COM at the bottom. So that stands for common ground. So no matter what you're measuring, the black wire is going to go in there. And that will connect to one end of this resistor. Why don't you take out the resistor that's 330 ohms for this? And then use your black cable to go from the common ground to one side of this. Remember, resistors are, they don't have preferred directions, so either side can be the negative side. And then for the positive, we know we're going to go to the other side of the resistor with it. The question is, which one of these other three plugs in the multimeter do we want to use? And we want to use the one on mine. It's red. It's all the way on the right, and it says voltage and resistance. So if you're measuring voltage or resistance, you want to put it over. You want to put the positive over here. Okay, so this says voltage and resistance, or I guess it says volts and ohms. And we're going to take the positive one and put it over here. And you can just hold it to the resistor with your fingers. We're doing things with such small amount of electricity, you won't feel anything. And right now you still have the dial set to 0. And so now that once you have it all in place, you want to rotate the dial to somewhere in that, we know we want to put it somewhere in that ohms section on the lower right. Well, the one that we want is always going to be, in every case, whatever measurement you're taking, is always going to be the smallest value that's still bigger than what you're measuring. Okay, so we want the smallest setting that's bigger than what we're measuring. Okay, so we're measuring something that's 330 ohms. The K's mean kilo, so that means times 1,000. The M's mean mega, so that's times 1,000,000. We can't use the 200 setting. That's smaller than what we're measuring. So we want to use the 2K, the 2,000 ohm measurement. So now that you have it all in place, rotate your dial to the 2K. And since it's in K, it's going to give you a value in kiloohms. So you're looking for something that's about 0.330 kiloohms. And it's not going to be exactly 0.330 because it's impossible to manufacture these things with perfect precision. And remember, that's what the gold and silver bands and stuff, the last colored line on those resistors says, is how close you can expect it to be to the desired value. But you might read, it might read 0.326 or it might read 0.338 or something. But it's going to be in the ballpark of 330 ohms. Okay, so let me just pause and then hook this up. Yeah, that's a reasonable guess. It would really just say there'd be an OL on the screen that says overload. And it just means that the value is bigger than it can represent on that scale. You might think that that would blow a fuse, but it doesn't. The screen just can't give a reading for it. So that's a pretty innocuous thing, mistake to make. But if you ever see an overload, it just means that you haven't chosen a big enough setting. Okay, so now let's measure voltage. So let's say that we want, so our circuit is going to be like this. And we're going to use a 9-volt battery. I'm going to put this in quotes because a 9-volt battery is not exactly 9 volts. And I'm going to use a 1,000 ohm resistor. I'm going to also put that in quotes because we don't know exactly what that is. And actually, let's use the 330 instead of the 1,000. Then you can use the one you just measured. Okay, so for a first step, measure the resistance of that resistor before you put that circuit together. If you remember what you got before, you can just write that down. And next, so if we're measuring voltage, remember what we do is we build the circuit and then we just hold the 2 leads of the multimeter across the terminals of whatever device we want. So you can think of like touching one lead from the multimeter to one wire from the resistor and the other one to the other wire in the resistor. So okay, I'm going to. Well, do you want to try doing this before I write anything up here? See if you can put this circuit together, and then I'll talk about what to do with the multimeter. Here are kind of the 2 extreme ends of options for doing this. The simplest way to do it, you don't need a breadboard or anything. You could just take this 9-volt battery and using alligator clips, you could just go, so that's supposed to be an alligator clip. And you could just go like this. and like this. The way that's sort of more useful for what we're going to have to do soon is if you have your breadboard, and let's say this is your positive power rail. I'll do that in red. And this is your negative power rail. And then these rows are all connected. So you could take your battery and take the positive and connect it to the positive power rail. And take your negative and connect it to the negative power rail. And now you can just kind of forget about the battery and you can just think about the power source just being those two rails for the rest of your project. And I'll put my resistor here. And now I'll connect my positive power rail to one side and my negative power rail to the other side. That's supposed to be the wire jumping over the red power rail. And if you set it up like this, either of these two ways, electricity is flowing through that circuit. Okay, well, let's do two things. Let's measure. They're going to give the same answers, but let's measure both of them independently. So first, let's measure the voltage in the battery. So with this circuit intact, so with the circuit closed, so electricity can flow. Press the positive lead of the multimeter to the positive battery terminal. And then press the negative lead of the meter to the negative battery terminal. And then we expect this voltage to read somewhere around 9. So look on your multimeter in the upper left quadrant into those voltage ones. And the smallest voltage that's still bigger than the voltage we expect is 20. So rotate that to 20 volts. And it should read a value somewhere around 9. Okay. Are you getting a value for that? This should all work because the voltage and resistance stuff, if the fuse is blown, it still works. It's only the current that gets affected when the fuse is blown. Okay, so what values did you get? Did you get one yet?
Do we attach the meter to the battery or to the?
Do it to the battery for now.
Okay. The battery's at 8.1.
Okay, yeah, that's about right. What did you guys get?
773.
Okay, yeah. So it'll vary a little bit. Also, we have current coming out of the battery, and remember I was talking about the car battery thing yesterday, that really a big battery, what it's good at is producing a lot of current. It's not really having a higher voltage. So as you draw current out of a battery, that voltage will go down, you know, and if we drew more current out of it, the voltage would go down more, and you would notice it on the meter. What did you guys get for a voltage?
9.15.
Okay. Yeah. So all different than 9, but all somewhere around 9. And now turn your meters off for a second. And let's do the calculation. Now that we know the voltage in the battery when it's in this current, and we know the resistance of your resistor, so let's do the circuit calculation. So for example, let's say that I'm going to use 7.84 volts from the battery, and I'm going to use a resistance of 322. And I'm going to solve this circuit. I'm going to calculate the voltage and the current in all of the devices that are attached, which in this case is just that resistor. Well, since the electric potential is the same all the way around the left wire, and it's the same all the way around the right wire, we know that the voltage here is going to have its positive over here, negative over here, and it's going to be 7.84. And we also know that the current is going to flow this direction, and we can use Ohm's law to calculate what the current should be. So I'm going to use Ohm's law. And it's going to say the voltage across that resistor is equal to the resistance times the current through that resistor. And so we expect that current to be in my case, it's going to be 0.02 0.243 amps. Yours is going to be different because you have different values of the resistance and the voltage. Okay. So now what we've done is make predictions about what we expect to see when we measure the voltage across that resistor and we measure the current through that resistor. So now take your meter and press the leads so you still have that circuit intact running. Press one lead of the multimeter to one terminal of that resistor, and the other lead of the multimeter to the other terminal of that resistor. Okay, and then again, switch the multimeter over to 20 volts and see if you're measuring a voltage of what you predict. Are you with me on this? So you're just touching the terminals. You're touching the leads of the multimeter this time to the two sides of the resistor. Are you getting that same voltage that you got for the battery?
Yeah.
Okay, yep. Yeah. So now we're going to measure the current through that resistor. Okay, so notice that with this simple circuit that we made, everything is in series. Okay, so like any electricity that goes through the battery has to go through the resistor. There's no other paths that it can veer off. And so the current is going to be the same anywhere. So it doesn't matter where we make a break in this circuit. But what you're going to do is somewhere in this circuit, if you did it this way, you can just disconnect this alligator clip to make a break. If you did it this way, you could move this wire down to this one to make a break. And then you're going to insert the two leads of the multimeter to complete that circuit using the multimeter. Okay, like when the train tracks break and Superman lies across it to complete the train tracks, that's what you're doing with the multimeter. Okay, so you make that break and then you fill it with the multimeter. And then once you do that, we've already estimated what the current is that we're going to get. And so go to the amps setting. Oh, and this time we're going to have to move the leads too. So let me draw this. So which one am I going to do? I'll do this one. Okay, so I'm going to imagine I have my circuit set up like this. And I am going to get rid of that. So right now the current is going from the positive of my battery to the positive power rail into the resistor. But I am going to make a break here that goes from the so now there's no way for the current to go from the negative terminal of the resistor back to the negative of the battery. Right now it's broken. No electricity is going to flow. Okay. And I'm going to now insert the meter into here. So I'll put the positive lead of the meter along this, and I'll put the negative lead of the resistor along this. And now current can flow through the resistor, through the meter, and back to the battery. There's one more issue we have to think about here, and that is where do we want to put the, so we know that the negative terminal of the meter is this common, and we want that to connect there. But we're going to have to plug the positive lead of the meter now has to be either in the amps or milliamps setting. Okay. We want a value of 0.024, well, that's mine, around 0.02 amps, which is about 20 milliamps. Okay, so look on here and see, do we want this in a milliamp setting or an amp setting? If we want it in a milliamp setting, so there's one that goes up to 20 milliamps. Okay, but that might be too low. It's right around what our value is. We might as well put it on the 200 milliamps. So since we're going to put the dial on the 200 milliamps, we're going to put the positive lead in the milliamps thing, not in the amps thing. Okay, so I'm going to put the red wire in the milliamps, and I'm going to connect to the positive, to the negative of the resistor. And now if you follow what the current is doing, now this current can flow as long as it goes through the meter. So it's going to go positive of the battery, into the resistor, through the meter, and back to the negative of the battery. And it should give us a value in milliamps that's almost exactly what we calculated here. Here's a question. What do you think would happen if so we were pretty careful to put the positive lead of the multimeter into the position where current is flowing in, and the negative lead of the multimeter to be where current was flowing out. What do you think would happen if you switch the order of those leads?
We did that.
Okay. And all that happens is it just gives you a negative sign, meaning that you have your lead switched. So for our purposes, that usually is perfectly fine. If you get a negative, it just means you have the leads. If you switch the leads of the multimeter, it would be opposite. That works with current, and it works with voltage that way too. Okay. The last thing I want to talk about today, I hope I have it here, is resistors in series. So series, I mentioned, any devices in series means that all the electricity that goes through the first one then goes through the second one. So all the current that goes through the first one has to go through the second one. And examples are like those two resistors are in series. So when two resistors are in series, the voltage of the battery is divided between them. So like, for example, in this case, if this was a 9-volt battery, depending on what the resistances are of these two resistors, one might have a voltage of 6 and one might have a voltage of 3. Okay, whatever the voltages of the two resistors have to add up to the voltage of the battery. Okay, so to use Ohm's law for these, for resistors in series, the first step is treat the two resistors as if they were a single resistor. And I'm going to call that the resistance of that one R equivalent. Okay, so everything in the red line up here, we're going to treat as if it was a single resistor with a resistance R equivalent. Okay. Then the resistance R equivalent is just equal to the sum of those two. Third, use Ohm's law to find the current through the circuit. So we're going to use Ohm's law with this equivalent resistance. Remember, the whole the defining feature of elements that are in series is that the current is the same through everything, because that electricity can't go anywhere. So we're going to find the total current through every element in this circuit. And then finally, we'll use Ohm's law for the individual resistors to calculate the voltages. Okay, so let me do an example. So let's say that we have this circuit where we have a 5-volt battery and we have 2 resistors. Let's say this one is 500 ohms and this one is 200 ohms. And we want to solve this circuit. Well, first we're going to imagine these. The first step is you have to identify that these are in series. So is there any way, anywhere that current can flow that goes through the 500 where it doesn't flow through the 200? And the answer is no. So these are in series. And so we're going to lump these two together as if they were one single resistor. And the resistance of that is 500 plus 200. So that's a 700 ohm resistor. Okay. If you wrap tape around both of those or whatever and sold it as a single unit, it would be a 700 ohm resistor. And so now we just have to solve that circuit. We've sort of updated it to this, where this is 5 volts and this is 700 ohms. We know the resistance, the voltage across here is 5 volts. And so Ohm's law says 5 is equal to 700I. And so I is equal to 0.007143 amps. Okay, we did that to calculate the current as if with these lumped together. But the thing about elements in series is that that's the current going through all of those elements. So now we can use Ohm's law for the individual ones. So now we'll go Ohm's law for the 500. And the voltage for the 500 is the resistance times the current that we just figured out. And that is 3.571 volts. Now we'll do the same thing for the 200. So the voltage across the 200 is the resistance times the current. Oh my God, come on. No idea what I just did. Okay. And that is 1.429 volts. And notice that if you add those two voltages up, you get 5 volts, the voltage of the battery. Okay, any questions about that? So I'll give you some problems to work on with the multimeter and with series resistors. And then we'll finish this stuff up and start talking about the robot project tomorrow. All right, goodbye.